Okay. All right. Hi, everyone. So my plan is to write on the board today. I know when I was sitting in the audience, I could not read what people were writing on the board. So if that's the case for you guys, just like let me know, and I don't know. I'll do my best. Okay. So, all right. This is more of high dim stats, right? Okay, so what did we learn last time, right? Okay, so last class, basically what we covered, right, is failure of classical asymptotics, right? So by classical asymptotics, I mean, dimension fixed in sample size growing. And we saw this even in, finite size problems, right? Okay, so it turns out at some level, this sort of like failure of the classical predictions due to high dimensional phenomena is sort of unavoidable, right? So if we think about classification, like the linear discriminant analysis example, it's like, if we take alpha where, kind of recall, we were letting alpha be this sort of undersampling ratio, right? So D over N converges to alpha, right? So if alpha is bigger than 0, then, in linear discriminant analysis and classification, it's like you can't achieve that classical rate, right? That classical rate assumes that eventually you can estimate the distributions well, and it turns out that that's sort of not the case. In covariance estimation, right, if alpha is bigger than 0, there's sort of no consistent estimator of the sample covariance, in, for example, L2 operator norm. And, in the example of non-parametric regression, right, in order to estimate that function well, we're going to have an exponential number of points in the dimension, right? So these are kind of like just failures, basically, of this high dimensional regime. So I guess the question now is like kind of how do we save ourselves, right? So essentially, okay, kind of like what we do in high dimensional stats is that, so how do we recover, right? And essentially the idea is to, we always assume some lower dimensional structure. Right, so basically we always assume or hope the data is endowed with some low dimensional structure. Right? And so, okay, so what I wanted to start off with is just to give some example, or to look back at the examples we did yesterday and see the kind of the ways that we might incorporate low dimensional structure into the problem that allows us to kind of get over these hurdles, right? So, okay, so if I look at the LDA example, right, so just to recall, right, what is this example, right? So I have kind of data from two groups, x1 through xn1, xn1 plus 1 through xn2, where, the first is a sample from some Gaussian with mu and mu1, variance sigma. The second is an IID sample from a Gaussian with mean mu2, variance sigma, right? And, we construct a test statistic that's basically just the log likelihood ratio where we've estimated, you know, the parameters of these two distributions from the data itself. Right, and so, okay, in this case, right, we had kind of the classical asymptotics said that if we look at the error of this test statistic, assuming an identity covariance. So here I'm going to assume that both of these guys are actually identity, right? This is, you know, kind of the simple problem that Kolmogorov studied in the 60s, right? So we had classical asymptotics that says this goes to the error as if we could estimate, you know, the two distributions exactly, right? So this is classical asymptotics versus, you know, Kolmogorov's high-dimensional asymptotics, which says, you know, that we now converge to some error that's strictly larger and depends on alpha, right, this kind of undersampling ratio. Oops. Okay. So the question, right, is, okay, so why does the classical asymptotics fail? Right, and you know, essentially the reason is that if we have a high dimensional problem, then you know, even with our samples, we're never going to be able to kind of estimate these means exactly, right? So kind of the idea is the following. If you look at something like, you know, the distance between mu hat and mu, right, this concentrates on alpha, right, which is just this undersampling ratio, right? And you can kind of convince yourself of this by like usual chi-squared type bounds, right? And so, I mean, what this implies, right, is that there's a constant level of error in your estimates of the two distribution, right? So constant level of error in the estimates. And, you know, for that reason, right, your classical asymptotics are overly optimistic, right? Because it suggests that you should be able to get those approximations exactly. Okay, so all right, so if we want to do classification and, you know, high dimensions, then like what do folks do, right? And so essentially, you know, in this, like if we take this example, the kind of the common thing to do in the literature, right, is to assume that these underlying means have some sort of sparsity, right? So instead of living in the full d-dimensional space, right, they live in fact in some subspace, right? So, you know, if mu has some low dimensional structure, right? So, you know, for example, it's sparse, right? Meaning just that only, you know, a handful of its elements are non-zero. Then, you know, you can improve your estimate using like very simple ideas, right? Like something like thresholding improves your estimate, and this is going to allow you to get back to kind of the classical asymptotic prediction. So if you know, our true mean has some low dim structure like sparsity, sample mean can be improved. If it's sparse, right, using some sort of thresholding. So like, as an example, right, I could recreate those simulations, right? So if I recreated, for example, if I recreated the simulations from last time, like, so recreate, sims with, where mu1, mu2, have only s equals 5 non-zeros, right? So it's like they're vectors of a bunch of zeros and 5 elements that are not. You could use as an estimator sort of a thresholded sample mean, right? So I'll call this mu tilde, which is like a hard thresholded version of the sample mean, right? Where, so this is, for I equals 1, 2, right? And here h lambda is my hard threshold function, right? This is just an indicator that x is bigger than lambda times x, right? So this is a function that looks like, well, if we look at lambda, negative lambda, right? It's 0 here, and then once you get outside of lambda, it's just linear, right? So this is the hard threshold. Right, and it turns out if you choose a threshold, like, so here I said lambda n, so if I take lambda n to be like square root 2 log d over n, turns out to be kind of the magic number. Then what you'll see, here is, in this example, classic asymptotics describe the error. Right, and in fact, in this situation, right, so classic asymptotics match the empirics when when something like 1 over n log d choose s, where s is my sparsity level goes to 0, right? So for s. Yeah.
Just one question. So you're applying this thresholding function coordinate-wise to the vector?
Yeah, sorry. Yeah. Yeah. R to R, but apply it element-wise to the vector, right? Okay. For s non-zeros and, right? Okay. Right, so, okay, so this says that, as long as we believe that, kind of the things we need to estimate live in some, lower dimensional space than our ambient space, as long as that lower dimensional space is kind of small enough, then we kind of recover, the classical asymptotic predictions. Okay, so if we look at like covariance matrix estimation, right? So cov matrix estimation, what might, I'll just kind of mention briefly like what might be the structure that's appropriate and what do we do in those cases, right? So here this is, recall this is data, IID from some PX with mean 0, and the thing we want to estimate is the covariance matrix, which is the expected value of XX transpose. So the question is, what kind of low dim structure might we assume, right? And then what do we do with it? Right, so what people, in the literature, right, what okay, you might assume that it's a diagonal matrix. That's a pretty strong assumption, right? It's kind of independence of your elements coordinate-wise, right? And there, of course, you wouldn't estimate with the sample covariance directly. You'd zero out the, zero out non-diagonal elements. Right, so a kind of looser assumption might be sparsity, right? So this just says, your sample covariance matrix, right? So this is R D cross D, right? Is going to have a bunch of zeros and maybe only a handful of non-zeros, right? And there you could do something like thresholding of the elements that we saw earlier. Right, they're kind of more complicated assumptions, things like, fast decay of the eigenspectra. Right, which is a kind of like assuming some low ringedness, right? And so there, there's kind of more complicated methods that would take advantage of that, right? Okay, so then the last example, right, we looked at kind of non-parametric regression, right? So how do we get around the fact that we need an exponential number of points? All right, so the final example, right, was non-parametric regression. Right, so what was the problem, right? Well, we have some data xi, yi, I equals 1 to n, or iid from some pxy. Right, and so these are kind of these are in RD. These are d-dimensional vectors. These guys we're just thinking of as scalars, right? And we want to estimate the regression function, right? So this is just the kind of conditional expectation function. Right, and so what we said last time is that this is hard without any other assumptions because, in high dimensional space, all the points are far apart. So, it's like if you get a new point and you want to be able to predict, y well for your new input x, essentially that point isn't going to be close to any of the guys in our sample, so we aren't going to have a good estimate of kind of the function at that point. So okay, so what kinds of structure might we add? Right, and essentially, there are various kind of ideas. One idea might be, all right, so I'm going to assume, instead of just having kind of this belong to like a general function class, right? Maybe, we have some sort of additive decomposition. Right, so you might assume that your function that takes in, your element x, which is, d coordinates, right, actually factorizes over those d coordinates, gi xi, right, where, you know, these are just like some univariate functions from some base class, right? This is the function that we'd like to estimate, right? And so why does this work, right? Well, this works, right, because we only need to estimate kind of d univariate functions now, right? So an example, right, is the linear model. Right, where, you know, these univariate functions are like theta I xi, right, where theta is some coefficient to estimate. Right, and so like philosophically, what are you doing, right? You're kind of doing one of two things, right? You're either assuming that your data literally comes from some sort of linear model, right? So you're either assuming that this P of xy describes a relationship that's like, you know, y equals x transpose theta plus noise, right? Or you're going to argue that, okay, well, this could be something more complicated, but I'm using a function class that, you know, can kind of uniformly approximate more complicated functions well when the problem size is large, right? So philosophically, there's kind of two ways to think about what's going on, right? Okay, so I'll just mention that, you know, more commonly, right, you know, folks would assume perhaps even like a sparse additive decomposition, where, you know, actually what you're assuming is that this function is not like the full, you know, a full sum of d univariate functions, but, you know, just, you know, some univariate functions belonging to some subset of 1 through d, right? And so, you know, here we're thinking of like some subset of 1 through d, right? And of course, this is like, you know, encompasses like sparse linear regression where, you know, many of these thetas are equal to 0. Okay. All right, so I kind of wanted to just give a little bit of a flavor of like, you know, how folks who work in high-dimensional statistics approach these problems, right? So kind of, you know, if you do high-dimensional statistics, what you do is you're going to make some sort of assumption on a low-dimensional structure. You're going to justify that in some ways. I mean, in many cases, right, like things like sparsity are well justified. Like many natural objects are sparse in the correct basis. So even like images, natural images, are generally sparse and once you find the right basis, right, and this is kind of like why our compression algorithms like JPEG and stuff like work, right? So, you know, as a person who works in high-dimensional statistics, what do? You kind of assume some low-dimensional structure, you justify it as a good assumption, right, and then you study like kind of what you can gain by sort of exploiting the low-dimensional structure of the problem. Okay, so for the rest of today, I just wanted to kind of like formally sort of go through the task of like learning a regression function and just kind of talk like about some kind of models and definitions and, you know, how we actually do the estimation and these sorts of things. So we have, you know, notation kind of set, and along the way I'll kind of talk about just like, you know, general approaches that folks take to actually solve these sorts of problems. And then, next week we'll kind of get into, AMP as an algorithm for studying these problems. That's the sort of plan. So, okay, so what I want to do now, right? So now is kind of formally introduce the task of learning a regression function from data. Okay. So I'm going to focus on learning a regression function, but it turns out that kind of like many of the problems we've considered are either fall into this framework or kind of small generalizations from this framework. So even if we think about things like matrix estimation problems, it's like, you can either think of, in some problems, it's as simple as just, okay, now the matrix is like a vector stacked on itself, or if we have some sort of, low-rank structure, we can kind of generalize these ideas to encompass those models. So even though we're talking about sort of a specific task of learning a regression function, it kind of encompasses like a lot of the kind of learning task that we might be interested in this world, I guess. Okay. So, all right, so just to recall the model, and I'll introduce some definitions. Right, so the model's kind of the following, right? So I'm imagining, some random variables, x and y, that are coming from some, x and y spaces, right? So often it's the case that y, is just kind of a scalar random variable, right? So this y space is a subspace of R, and this is going to be called like the response variable, or in classification problems, it's a label. It's also kind of like called the output or the outcome. There are many different names, right? And x is going to be a vector, right? And RD, right? Which we might call like the covariates, are the features, the input variables, and so on. There's like, many different communities study this problem, and every community calls it like something different, is kind of how it turns out to be, right? Okay, so then the goal, right? Our goal is one of prediction, right? So given a new sample x, we want to predict y, our label or our response, right? And so, right, the statistics problem is the following, right? So if we knew the joint distribution of x and y, right, then the problem would be done. I predict y using the conditional distribution of y given x, right? And we could all go home. But the issue is, right, for statisticians, we don't know the joint distribution. We just have a sample from the joint distribution. And so, we want to still be able to predict y, but using this, using our data, right? Okay, so the object that we study, and I'll kind of motivate why this is the correct object to study in a moment, is the regression function, right, we talked about this yesterday, right? So the regression function is what, right? It's just the function that calculates the conditional expectation at any possible x value, right? So this is kind of the summary of the conditional distribution that's of interest to us, right? Okay. And so if we're thinking about kind of a candidate function to describe the relationship between x and y, so kind of a candidate estimate of our regression function. So if I just take a general function g, you know, that takes as input my x's and spits out a y, right? We usually study the performance of g as a predictor by studying the L2 risk. So we usually study the L2 risk of g, which is just defined in the following way. The L2 risk is just the expected value of y minus g of x squared, right, where this expectation is over xy. Right, so I'm assuming, like, you know, the expected value of y is finite. Right, so why do we study this? I mean, roughly, it kind of tells us, you know, roughly this L2 risk measures how close g of x is to y. Right, so you know, how do I motivate this, right? Why is this the correct measure of closeness, right? So if I suppose, you know, I know my conditional distribution, right? I want to predict y from some candidate x. You know, how do I do this? I want to find a g such that, you know, g of x minus y is small, right? All right, so I want to find a candidate g such that the difference between, you know, g and x and y is small, such that this is small, right? Why is this kind of the object of study, right? Well, the idea, right, is this is a random variable, right? So how is a random variable small? You know, this is sort of an arbitrary justification, but you know, we might say that, you know, a random variable z is small. You know, again, these are all kind of like, you could argue other ways too, right? But a random variable z is small if, you know, the expected value of z squared, which is the expected value of z squared plus the variance of z, is small. Right, so why is that, right? Because, you know, if we make the expected value of z squared small, then it means, like, we need the mean to be small and the fluctuations around the mean to be small. Right, so this is kind of one justification for choosing L2 risk, right? The more honest justification of choosing L2 risk is that it's, like, easy to work with mathematically. But, you know, you have to make some choice, and this is the one that folks generally make. Okay. The reason this is is useful mathematically, you know, well, one of the reasons this is kind of a nice object to work with mathematically is the following fact, which says that, you know, the best predictor, so the best function g, you know, from, you know, our x space to our y space, so the best function g in terms of the L2 risk, is the regression function. Right, so in other words, I mean, the following, right? So if I want to, you know, minimize this guy over g, right? So if I take the inf over measurable functions g of my L2 risk, this is going to be equal to, you know, well, the minimizer is the regression function. Right, where this is f of x equals my conditional expectation. Okay, so I'll write a quick proof of this. It's really straightforward. But this, you know, kind of a lot of high-dimensional statistics rest on this sort of fact, right? So a lot of what we end up doing is putting tons of effort into trying to estimate this function, you know, because in some sense we think it's the optimal one. Right, so, okay, so here's the proof. Right, so if I take any g, you know, for any g, if I look at its L2 risk, right, this is just the expected value of y minus g of x squared. Right, then I can decompose that in the following way, right? So I'm just going to add and subtract my regression function, and then I'm going to expand the square, right? So what do I get? All right, so expected value of y minus f of x squared, so this is the L2 risk of the regression function, plus, you know, the expected value of the difference between f and g squared, plus my cross term, right? And so the claim, right, is that this cross term is equal to 0. Right, so claim that this is equal to 0, and why is that the case? Right, well, why, if we just iterate the expectation, it's not hard to see, right? So expected value over x, y of this cross term y minus regression function times regression function minus g, right, is the expectation over x, expectation over y, sorry, yeah, y given x, right, y minus f of x minus g of x, right, but we're conditioning on x here. right? So kind of the idea, right? We're conditioning on x, so this guy comes out, this guy is constant. So what do we have, right? Well, we just move this expectation onto the y, right? So this is expected value of x, expected value of y given x minus f of x times f of x minus g of x, right? But this is how we defined f of x, right? It's just my regression function, so this term equals 0, right? Okay, so
Can I?
Sure.
1 second. What do you mean by a random variable is small if the variance is small because the random time is equal to the factor? I mean, the variance is.
Right. So okay. So what we're using as our definition of small, or our measure of smallness, is this, right? So this is kind of the idea is, I'm thinking of this random variable as z, right?
Okay.
And so I'm arguing that studying this as an object is kind of a reasonable thing to do if I want, this difference to be small, right?
Okay.
And so I'm saying, I'm thinking that a random variable z is small if the expected value of z squared is small.
Okay.
Why? Because, okay, well, roughly that implies that both the mean is small and the fluctuations around the mean are small.
Okay.
I mean, this is hand wavy, right? And you could argue other ways, but, sort of because this implies both mean of z and fluctuations around the mean are small.
So you want the second order to be.
Yeah.
Okay.
I mean, kind of the idea is why not, the first moment, or why not, well, we'll kind of discuss other kind of ways you could choose to study kind of, I mean, the whole thing is, right, I'm going to use this as a basis for choosing a good G. And it's why is this the right thing to study? And I'm trying to give some sort of motivation.
Great.
Yeah.
But does it make sense to think about, I mean, if you say that you want to choose the L1 risk, you would want to be you would want the first moment to be small, or it has, or it has nothing to do.
Yeah, I mean, the random variable I'm thinking about, right, is kind of this difference, right? So it's, I mean, it's a little bit odd to think, I mean, I think it's not so natural to think about moments of this object is kind of the
Well, I mean,
idea.
if you choose the risk, you would anything else to be small.
Wait, say it again?
Okay, I think I'm a little bit confused.
Yeah. So I guess all I'm trying to do is motivate an arbitrary choice, right?
Okay.
You could argue that, so what I'm trying to say is, I'm kind of introducing definitions now, so the story's not quite complete, right? But, basically the object that we're going to want to study is this, because it's the function that minimizes this.
Yes.
Why do I care about minimizing this? Well, I want whatever my function is on x to be close to y.
Yes.
There are many ways that I could kind of say that this, g of x is close to y, right? I have to choose one. This is the one that the literature chooses. And I'm trying to give an argument that's not just like out of mathematical convenience we've chosen L2 risk, but perhaps that's like the most satisfying of the arguments, as it turns out. Yeah. Right, but the fact at hand, right, is that if we choose the L2 risk, then it's this regression function that minimizes it, right, that gives us our best sort of predictor. So just to kind of wrap this up, right, so what we've shown right, so okay, so we've shown, right, so if I look at, the risk of some function g, right, where again, this is the L2 risk, right, this is equal to the risk using the regression function plus the squared distance between the two. Right, so in particular, the risk of a function g is going to be greater than or equal to, the risk of the regression function. Right, and in particular with equality, if and only if, f equals g. Almost everywhere, right? So, right, so, okay, so this says if we choose this notion for kind of goodness of fit of our function mapping between the covariates and the output, right, then the regression function is kind of the object that is our best predictor, right? Okay, so right, so this this is why it's in general called like regression, right? This is why statisticians study regression, because what we're trying to estimate is this regression function for precisely these reasons, right? So, okay, so of course, right, in practice, we don't know the regression function, right? We don't know y given x, or this regression function. But instead, we observe, our data xi, yi, I equals 1 to n, right, that are IID from this unknown joint distribution. Right, so, essentially our goal then is to construct an estimator using the data right, that I'll call Fn hat. I'll make this clear in a minute, right, from our input space to our output space. So we want to construct this from the data with small L2 risk. Okay. Yeah. Oh, sorry, hey. So, you know, it's one of these things that, like, if you want to assume the distributions of X is known, folks are generally okay with that. You know, there's kinds of different, like, you know, it's like if we're really thinking about a real data set, you know, it's probably better to work with like deterministic kind of ideas about X. In general, when you're doing theory, it's kind of more convenient to put some randomness in it. I think for now, I mean, we can think of it as either way, really. It doesn't matter so much. But I think in general, people are comfortable if you want to put assumptions on P of X. Though, I mean, you know, if you really want to be a statistician, right, you have to be pretty liberal with those assumptions because it has to, you know, be an assumption that's reasonable for like your data and practice, right? And if you have data on, I don't know, kind of health measures of an individual or something like this, what's the correct, you know, random assumption? It's a little bit, you know, there's a lot of questions there, but I think for us it's like if we want to assume P of X is known, that's fine, and we will at some points, you know, or in particular like all of the AMP theory I will tell you about at least is going to assume that the X's are IID Gaussian, which is not a realistic assumption if you actually want to model data, but does allow you to do some nice theory. So, yeah. Okay. If yeah, just feel free to like yell at me if you have questions. I like sometimes I'm just like, you know, in my own head up here. So, okay. So, all right. So the first thing I want to just, you know, remind ourselves of is that if we want to make a small L2 risk, then this is equivalent to just looking at kind of a small deviation from the regression function itself. So kind of the idea is that usually when you know, think about constructing estimators, we don't, you know, at least the statisticians don't do it by trying to minimize L2 risk directly. They minimize something called the estimation error, which is basically just, you know, F minus Fn hat. And the reason is that they're like equivalent kind of notions or equivalent things to optimize, right? So basically the idea is from the earlier proof you know, if I'm trying to find a function of the data that has small L2 risk, right, I can look at this L2 risk, right, and it's just equal to the risk of my regression function plus what we call the estimation error. Right, so, all right, so this we generally refer to as the estimation error. Right, and so sort of the idea is, you know, if I'm trying to find a good function that minimizes the L2 risk, right, this doesn't depend on, you know, doesn't depend on Fn hat, right? So minimizing the L2 risk over all possible functions of the data is just equivalent to minimizing the estimation error, and I think it's like, you know, a part of human nature that when we're trying to optimize something, we'd rather optimize something that like can feasibly go to 0, right? So generally, you know, if you read papers and these sorts of things, this is kind of the object that they sort of try to bound and these sorts of things, right? So kind of the takeaway here, right, is finding an Fn hat to minimize the L2 risk is equivalent to minimizing this estimation error, right? I'll just underline that. Right, so this is measuring in some sense the distance between the true regression function and our approximation of it from the data. Okay. But, okay, I'll mention here, right, so when we look at this estimation error, right, this is now, this is a random variable, right, so this is a random variable. Why? Right, because I'm averaging over x, which is like the input to these two functions, but my Fn hat has been generated from the data, right? So now there's like, you know, in x, y samples that add randomness here. Right, so if we're, you know, kind of the idea is if I'm trying to find a, you know, a function of my data that optimizes this, you know, I need some sort of deterministic summary in order to compare the size of estimators, right? So if I have like F1 hat and F2 hat and I want to say which one's better, right, you know, we can't compare this directly because it's just two random variables, right? So kind of, you know, to find good Fn hat, right, so good, you know, estimates from the data need a deterministic summary to compare the size of the errors, right? The size of the errors between, you know, for example, F hat 1 of n and F hat 2 of n. Okay, and so, okay, so I'm just gonna list a few ways that people would, you know, typically kind of summarize the estimation error in order to lead us to optimal estimators. Okay, so, all right, so let's, so I'm just gonna call phi of n, I'm just gonna let this be, you know, a sequence of positive numbers that goes to 0 as n grows. Okay, so there's a number of ways that people will, you know, typically compare estimation error right, so okay, so one thing that folks might do is put bounds on the expectation, right? So you actually just average over the data as well, and you want an upper bound on that, right? So this looks like something like the expected value over the data, then you have the expected value over kind of the new input of f of n hat x minus f of x squared less than or equal to phi of n. Right, so this is kind of like the average the average behavior of the estimator over multiple realizations of the data, right? So, you know, one way that, you know, you have your favorite estimator, right, you might justify that this is good is by showing that, you know, this sort of expectation is small, right? The issue is that it shows that kind of the mean is small, but it doesn't tell us anything about the tails or the fluctuations around the mean, right? So kind of a more useful sort of way to compare estimation errors is through bounds in high probability. Right, so this is something like if, you know, you look at the probability over the data of, you know, this expectation, this estimation error bigger than some given delta, right? We want this to be less than or equal to delta, you know, so for all delta in some range maybe. Right, so this controls now the tail of this sort of overall expectation, right? And so, you know, okay, I mean, like a remark, right? Remark is that these sorts of high probability bounds, right? So 2 follows from 1, right? So if you have a bound on the expectation, you can get this sort of bound on high probability if, you know, along with some sort of concentration inequality, right, from Gabor's book or something, right? So, you know, these will follow from a bound on the expectation as long as you have, like, you know, exponentially fast concentration to the mean or something of that nature. Okay. The other way you might compare estimation errors, and this is something that we'll look at when we study AMP, right, is through sort of exact asymptotic statements. Right, so this is something more like, if you look at the limit, you know, I'm thinking of in n and d2, right? Something like phi n inverse of this expectation. Right, so these are just kind of all ways that people might justify choosing, you know, some way to estimate the regression function from the data by like kind of looking at these sorts of statements to justify the goodness. Right? here I'm being a little bit vague, right? So, this is something that's going to 0 as n grows, but I haven't really specified anything about the dependence on the dimension, right? So even though this goes to 0 as n grows, if we're thinking about the dimension growing too, it's often the case, right, that this doesn't actually go to 0, right? And it goes to some constant, but it's hard to say something completely general. Okay. So I think maybe in the last little bit, what I'll do is I'll just make a mention about other choices of error, and then next time we'll talk a little bit about, in general, like how do folks actually find, like how do you actually estimate Fn? What do we do in practice? How do we sort of get here? And I've said nothing yet about kind of incorporating low dimensional structure or anything like that. So we'll talk a little bit about like how that's actually done. But maybe in the last 20 minutes or so, I'll just talk a little bit about other measures of error. Okay, so other measures of error. Okay, so all right, so I chose L2 risk rather arbitrarily, right, and got a little bit called out on it, right? So we'll consider other ways that we might be able to formulate this problem, right? So, I mean, kind of like the idea, is we chose the L2 risk. It motivates the regression function. Once we have the regression function, it turns out that what we can study is just this estimation error, and the story is a little bit tidy, right? And we can choose other kinds of ways, and they're also well reasoned, especially if you are in situations where you might have like outliers in the data, or these sorts of things. But the more or less the story becomes like messier if you choose other measures of error is kind of the TLDR version, right? So I'll also mention that when you read papers, like kind of the objects that folks will study, right? So you read a theory paper in high dimensional statistics, the main result, right, is going to be either like a statement like this for a specific problem, a statement like this for a specific problem, or a statement like this for a specific problem. And it turns out that, depending on the community, there might be slightly different forms of the main result. So in particular, I think statisticians tend to like statements about the estimation error, right? So statisticians tend to like bounds or asymptotics or these sorts of things on estimation error, where we're looking at some distance between the estimator and the regression function, right? So now I'm being vague about the distance, because we'll think about other measures, but in what we've just said, it's that one, right? And so I think statisticians like This because generally they want to do inference, right? So they want to actually, learn kind of properties of the underlying distribution and use that to kind of interpret the world or the science that they're studying, right? If learning theorist, right? So if you're reading something from like NeurIPS or Colt, they tend to like bounds on the risk. I'm being like really reductive, right? But this is, I think this is true, right? So they tend to like bounds on the risk of the estimator, right? And I think this is because they're generally more interested in prediction, right? So they just want good estimates of Y coming from the input data, right? Whereas statisticians are kind of more interested in doing inference, so, saying something about the parameters that generate the problem, right? In the case, of course, right, where we use L2 as our loss measure, these are sort of equivalent, right? There's a constant additive difference between the two. So this distinction doesn't matter, but if we move to other types of error, there's no guarantee anymore that we have like this, kind of nice equivalence between the two, right? So I'll just mention some other choices in the literature. Let's look at the distance, or I'm calling it a distance, but it could be like a pseudo distance, right? So there's kind of pointwise type bounds that people will give. So pointwise would say something like, if we look at pointwise error, it's like given some specific point in our input space, what we want to be small is, the distance between our estimator and at that point and the regression function, right? Other folks might look at a soup norm error, right, where now you just look at kind of the biggest error in the sample space, right? These are kind of common things that one might see. The other thing is like an LP error, right? For P greater than or equal to 1. I think like the most common is, of course, just P equal to 1, besides P equals 2, which is the most common, right? But then you look at an estimation error with this LP. Okay, so, for us, we'll mostly care about like L2 error because it has like nice properties, but, these are other things like, if you do a deep dive in the literature, you'll see all these different, at least these are different error metrics that you'll come across. And I'll make a remark, right, that the L2 error, right, that we've been studying makes the most sense when we're thinking about the output Y as being a continuous random variable, right? So if I'm thinking about a problem in classification, right, so for classification, right, where Y, is like, represents some labels. Do you know what I mean? So if I'm like trying to guess whether it's a picture of like a poodle or fried chicken or something, right? This is a classification problem. And so there, it doesn't make so much sense to use like L2 risk, right? You would do something like you might use might use a risk like the following, right? So your risk of a classifier H might just be the probability that, you know, y is not equal to your output, right? So for a classifier H from, sorry, input space to 0, 1. Okay, and then I'll just, I'll make one more kind of remark, I guess. Okay, so as a specific example, let's just look at linear regression. So as a specific example, right, let's consider a linear model. Right, so by this I mean, okay, I'm going to let my x space be Rd, and I'm going to assume my regression function is just equal to, you know, the inner product, you know, of its input with some coefficient vector for unknown theta in Rd. Right, so in other words, right, I'm assuming that the joint distribution on x and y is kind of determined by, you know, y equals x transpose theta, where theta is unknown, right? It could be any vector in Rd, maybe plus some noise, right? So, you know. Right, so if you assume a linear model on the data, this is generally what is meant by that, right? And in this case, the regression function, right? So conditional on x, I mean, assuming my noise is mean 0, right? Conditional on x, my regression function is just is x transpose theta, right? Okay, so in this case, right? You know, we were thinking about estimation error. Right, or more generally, kind of like expected estimation error, right? And it would look something like, you know, expected value over the data, expected value over x of, you know, the difference between my regression function, so this is x transpose theta, minus my estimate, which in this case, right, I'm going to call it just a theta n hat. Right, so this guy's squared. Right, so in particular, this is like the expected value. Data x transpose theta minus theta. Right, so in this situation, it's also common that you might like measure kind of the error in your estimator directly on the coefficient itself, right? So, you know, in like such a parametric setting, it's also common to, you know, study error directly on the coefficient. Right, so by this I mean, you know, like if, you know, my estimator, so if fn hat of x equals x transpose theta n hat, right? So this theta n hat uses the data, right? Then, you know, then may study something like the distance between theta n hat and theta, e.g., you know, the norm of theta n minus theta squared would be a common thing to see in the literature, right? So kind of the point is, you know, if you assume a lot of structure on the problem, then sometimes, you know, you take a more kind of specific, or folks will study like a more specific error metric directly on kind of the coefficients that you're estimating. In some sense, like studying, you know, this is kind of equivalent to making, you know, some assumptions on the input x here, right? If, you know that distribution or something, then you kind of pop out that sort of error. Okay, so I think maybe I'll stop here for today instead of trying to cover the last bit that I wanted to, and then yeah, on Monday I'll kind of wrap up this discussion, just sort of introducing the problem and these sorts of things, and then we'll get started with the IMPA stuff afterwards. So happy to take any more questions if there are any. Otherwise, we can go to lunch. Thanks.